Hello everyone, welcome to Reality Statistics for Data Science. Today we're going to talk about confidence intervals. The goal is to quantify the uncertainty associated to a certain statistical estimate. The prerequisites for this material are expectation, Chebyshevs inequality, and the central limit theorem. Okay, so what is a confidence interval? A confidence interval is a random interval, which the way we're expressing it here is centered at a certain random variable w, but that doesn't need to be the case, okay? You can just think of it as a random interval, such that the quantity of interest that we're trying to estimate, in this case gamma, this will be the population mean in our examples, satisfies the following. The probability that this quantity of interest gamma is within the random interval is lower bounded by 1 minus alpha, which you can think of as 95%. It typically is 95%, it could be 99%, it could be something different if you choose it that way. In most scientific articles, it's 95%. So 95% of the time, the actual quantity that we're interested in is within the interval. I want to stress from the beginning that here the only random quantity is the interval, because it depends on this random variable w. The rest, in particular the quantity that we're trying to estimate, is actually deterministic. So we shouldn't get confused by that. I will return to this point a little bit later on. We're going to focus on building and understanding confidence intervals for the sample mean. So the idea is that we have n IID random variables. For example, we might have sampled n people from a population, and we have measured some quantity about them. What we really want to know is the population mean, so the mean of that quantity over the whole population, but we only have access to this n samples. Okay, so in that case, we already saw in a previous video that we can model this as IID random variables that have a certain mean and a certain variance. And now in order to build our confidence interval, we're going to assume that the variance is bounded by a certain value b that we know, because the point here is that we're going to need to make some assumption about the population variance in order to be able to construct a confidence interval, but we don't know this population variance. So we're just going to assume that we can bound it in some reasonable way. I'll show you an example in a moment. Okay, so what is going to be our estimate for mu? Our estimate for mu is going to be the sample mean. No surprise there. Again, you pick, for example, n people out of a population. You want to estimate the average of the whole population, the population mean. It's very reasonable to just average that subset of people. And now we're going to try to establish what uncertainty we have about that estimate, depending on the value of n, depending on how many people we're averaging over. That's what we're trying to do. Okay, so again, our goal is to quantify the uncertainty in our estimate of the population mean when we use the sample mean. Our first tool that we're going to apply to this is Chebyshevs inequality, which allows us to construct a confidence interval that holds for sure. I'll explain in a moment what I mean for sure. This is in contrast to the central limit theorem, which just gives you an approximate confidence interval. What does Chebyshevs inequality say? It says that random variables with small variance cannot be very far from their mean with high probability. More precisely, the probability that there's a deviation of c, a squared deviation of c from the mean, is bounded by the variance divided by c for any positive constant c. We're going to apply this to build a confidence interval for the sample mean. The confidence interval looks like this. Remember, b is the bound, actually this is a b. Okay, we're going to do as if that's a b. I'm not going to re-record the video. I hope you're okay with this. Again, b is a bound. I thought I had corrected this, but typos are just the bane of my existence. Anyways, alpha is such that we want the confidence interval to be a 1 minus alpha confidence interval. N is the number of people that we're measuring, and m is the sample mean. Okay, so we want to show that the population mean, which by the way is completely deterministic. Okay, we'll see an example in a moment. It's just whatever the population mean is, it's fixed. What is the probability that it belongs to this interval? Why is the interval random? Because the sample mean is random. Why is the sample mean random? Because we're choosing people at random from the population. So sometimes we might get unlucky and the average of the people that we choose might be super low or super high. Like this could happen, right? We're just trying to show that that won't happen with high probability. Okay, so again, the randomness comes from the sample mean. Okay, so I will fix the typo at the end. Let's live with it for now. What's the probability that mu is within that interval? It's 1 minus the probability that the deviation between m and mu is greater than this quantity here, okay? So now let's try to bound that probability. And for this, we can just apply Chebyshevs inequality. Let's put a square here, and let's put a square here. We can interpret this as C. So this is going to be bounded by the variance of m divided by C. And that's where we're going to need a bound on the variance, which makes a lot of sense, right? Because without any assumptions on the variance within the population, if the variance is huge, then the sample mean is not going to be very meaningful. We actually, I did a video about this before, when you cannot trust the sample mean. So we do need to make some assumption about the population variance. Okay, so that's bounded by the variance of m divided by the square of this quantity, which is that constant. And now we apply our bound on the variance, which is b squared here. So, okay, that's the population variance. We apply the bound on the variance, and things cancel out so that we get alpha. So indeed, the probability that the population mean is within that interval is lower bounded by 1 minus alpha. And now is when I will fix the typo again. And again, I'm sorry about that. Okay, so Chebyshevs inequality gives us a strict confidence interval, meaning that it holds for sure. Okay, the probability cannot be smaller than 95%. The probability that the population mean is within this interval. That's the good news. We're going to see the bad news now. The bad news is the following. Okay, so the height data that we had considered, we measure a certain sample mean of 176 centimeters. Realize that here I'm not putting a squiggly line because this is not a random variable. I've just measured it once. Boom, 176 centimeters. Now I want to know what the uncertainty associated to this estimate. So I want to build a confidence interval for it. I need a bound for the standard deviation. These are heights of adults. So the difference between the mean and the tallest adult and the shortest adult is going to be around, is definitely bounded by 75 centimeters. So, the mean is around 170 centimeters. The deviations are not going to be more than this, right? Like the tallest person that I can think of, people that play in the NBA are 2 meters 20, something like that. The shortest adults that I can think of are like about 1 meter 40. Maybe there are shorter people, but let's assume that this is a reasonable bound on the standard deviation. Okay, we plug it into our formula for this value of the sample mean, and boom, we get 142.5 to 109.5. This is not ideal, right? Like, of course, the mean of the population is within that. This is completely driven by our bound on the standard deviation. So it's actually often the case with Chebyshevs inequality, and we already saw an example before when we discussed Chebyshevs inequality. This is usually the results obtained from Chebyshevs inequality are usually extremely conservative. Why? Because they don't exploit the fact that the sample mean has a very, very well behaved distribution. It's in particular, it's Gaussian-like. It only assumes some kind of bound on the variance. Okay, so that's why this confidence interval is huge and therefore useless. And that's why people in practice do not use Chebyshevs inequality to build confidence intervals, even though, it is a strict, like it's definitely true that the population mean is going to be within that interval, within the interval constructed with the Chebyshevs inequality, not within that particular interval, within the interval constructed with Chebyshevs inequality. with a certain probability. Again, I'll come back to the interpretation a little bit later. But the point is that this interval is not great. It's too large. So how about we use the central limit theorem, which tells us that the sample mean is behaved in this very nice Gaussian-like way. Okay, let's go ahead and do it. So what does the central limit theorem tell us? It tells us that when you have IID random variables with a certain mean and a certain variance, the sample mean tends to be Gaussian with mean mu, where mu is the mean of each of the random variables, and variance, which is the variance of the random variables divided by n. Alternatively, you can normalize the sample mean so that not normalize, standardize. So you subtract the mean and you divide by the standard deviation, and that yields a Gaussian that has mean 0 and standard deviation equal to 1. Excellent. What is the problem? The problem is that we cannot actually apply this result as is in practice because we don't know the standard deviation in the population, so we cannot compute the standard deviation that these Gaussians should have. So what can we do? Well, we can be pragmatic and just use the sample standard deviation that we measure from our data. That's not going to be an exact measurement of the standard deviation in the population, but we hope that it will be close enough. In general, it will be close enough if n is large enough and the fourth moment is bounded. Okay, the fourth moment is just the expected value of each of the random variables to the fourth power. By the way, this makes a lot of sense, right? Because when does the sample mean converge? When the variance is bounded, and the variance is related to the mean square. Okay, so when is the sample standard deviation going to converge? When its square, when the expected value of its square is bounded. But anyways, this is a reasonable choice. There are corrections you can make when n is not that large, using other distributions that are not the Gaussian, but we're not going to discuss that now. We're just going to go ahead and use a central limit theorem where we use this estimate of the standard deviation. Okay, so this looks a bit scary, but let's take it, step by step. I'm saying here, and this is very important, this is an approximate confidence interval because we're using this approximation. We're assuming that the sample standard deviation approximates the true standard deviation, and also that the central limit theorem holds, and it only holds in the limit. Okay, but we have seen previously that it's actually like quite precise even for moderate numbers of n. Okay, so first let's parse this expression. This is the estimate of the standard deviation. This is the sample mean. This is the number of measurements that we're taking. And this is the CDF of the standard Gaussian. So we'll see of a Gaussian with mean 0 and standard deviation equal to 1. We'll see now why it appears there. Okay. Again, we're trying to estimate mu. This is a deterministic quantity. The only things that are random here are the sample mean, because we're choosing people at random, and the sample standard deviation. Again, because we're choosing people at random and computing it in that way. Okay, so now what we're going to do is we're going to move things around. When we move things around, we move, before we move things around, I got ahead of myself. What's the probability that mu is within this interval? It's 1 minus the probability that it's out of that interval. So here we see the probability that the sample mean is above mu plus this quantity, and we also need to subtract the probability that the sample mean is lower than mu minus this quantity. Okay, and you can check that. If that happens, then mu is not within the interval. Okay, so now we have to bound these two probabilities. And in order to bound them, what we do is now we move things around. So we put like the mu to the other side. We divide by this on both sides. And when we do that, we get this expression where this is the standardized version of the sample mean, where we have subtracted the population mean and divided by the standard deviation of the sample mean. And this is an approximate standard deviation because it uses the sample standard deviation as opposed to the true population standard deviation. And again, by this modified version of the central limit theorem, we're going to assume that this thing is a Gaussian with zero mean and unit variance. Okay, so now we have the probability that a Gaussian with zero mean and unit variance is larger than a certain value or smaller than a certain value. So the first thing to realize is that we have the same value here and here, except that there's a minus here. So if I draw, and you know that I'm not very good at drawing, but let's see. Okay, let's try to make it a little bit more symmetric. Okay, it's not going to get much better than this. So on the one hand, we have the probability of being above a certain value. Let's call the value, I don't know, beta, where this is beta. And on the other hand, we have the probability of being smaller than minus beta. So by symmetry of the Gaussian distribution, these probabilities are the same. So we can just focus on the probability of being here, greater than that particular value. And that's what we're going to do. We're going to focus on that probability. Okay, so what's the probability that this Gaussian is larger than this value? It's 1 minus the value of the CDF at that value, right? What's the value of the CDF here? Well, this is the inverse CDF. So this is just going to be 1 minus alpha divided by 2. This is not a coincidence. So this is just going to be equal to alpha over 2. So the probability that we're above, so the probability, let me go back to the picture. The probability that we're here is alpha over 2. The probability that we're here is alpha over 2. And that's awesome, because then the probability that we're in the middle, so which happens when the population mean is within the confidence interval, that probability is 1 minus alpha. 1 minus alpha half minus alpha half is equal to 1 minus alpha. Okay, so this shows you that if the assumption holds that this quantity is indeed well approximated by a Gaussian with zero mean and unit standard deviation, we have an approximate confidence interval for the population mean. Okay, so again, the probability that the population mean is in that confidence interval is equal to approximately 1 minus alpha. Okay, so let's apply this. Again, I get this measurement of 176 centimeters and a standard deviation of 7 centimeters compared to the bound on the standard deviation that we had before, 75 centimeters. And we're going to use the fact that the CDF at 1.95 is 0.025. Because we want a 95% confidence interval, so alpha is equal to 0.05 and alpha half is therefore 0.025. So now we plug in everything in this confidence interval that we have been working with, and we get something that is much, incomparably better to what we had with Chebyshevs inequality. Okay, so now we can produce this estimate for the sample mean. We say, we think the average is 176 centimeters, but we provide this confidence interval, which is 174.6 to 177.4. But now we have to be very careful about how we interpret this, because you could be tempted to say, well, the probability that the mean height in the population is between 174.6 and 177.4 is 0.95. This sounds, very reasonable. It's a 95% confidence interval, right? So this is what it means. Okay, now I want you to look at this, read this, and think what is wrong with this expression. Go ahead. So what's wrong with this expression? Pause the video and think a little bit about it. If you get anything from this video, it should be this. Well, the issue is that, let's go one by one. The mean height in the population, this is fixed. In particular, for this data set, the actual mean height, I wish I remembered it, but let's say it's 176.6, I think, or something like that. So it's actually fixed. It's a deterministic quantity. It's not going to change. the average height of people in New York, not going to change. It is what it is, it's fixed. And then we say it's between 174.6 and 177.4. Those are also fixed quantities. So either it's in or it's not, right? In this case, it's actually in, because I remember that it was roughly 176.6. So it is in. So what is this probability? What does that mean? What it means is that if I repeat this procedure and I produce confidence intervals like one after the other, when I've produced like about 100 confidence intervals, and they don't have to be about this particular data set, like you could get a bunch of like scientific articles saying, oh, you know, the average cholesterol for these people is within this confidence interval, 95% and so on. You look at all those confidence intervals, 95 out of 100 are going to be correct in the sense that the true quantity that we want to estimate is within the confidence interval, and 5% of them are not going to be correct. So in this case, we can actually visualize this in the following way. I can repeat my procedure, right? Like here I picked, actually I'm not saying how many people I picked. I think I picked 100 people. But yeah, actually, I don't know why I even needed to commit here. I think here I picked 100 people. Actually, in the example, like in what I have in the following slides, I will tell you what n is. But like I picked n people, so I can pick n people over and over and over again, and then see how often the confidence interval indeed includes the population mean that I'm interested in. Because I do have a ground truth for the population mean in this case. Because we have this nice data set that we're working with where we can actually compute the population mean. So let's go ahead and do that. Okay, again, here n equals 20. These are 40 confidence intervals, and we see that this guy does not include the population mean. Actually, this is, so I was wrong actually. The true population mean is 175.6. It's not 176 point something. So in this case, we're pretty lucky. Out of 40, only one is out. Right? The other ones are all in. And again, each of these lines, what does it represent? It represents I took 20 people, computed the sample mean, computed the associated confidence interval. In this case, I was just unlucky. I picked very tall people. In this case, I picked quite short people, but it was fine. Like the population mean is still within the confidence interval. What happens when we pick more people? When we pick more people, the confidence interval shrinks, but we're still interested in a 95% confidence interval. So the probability that the population mean is within the interval is still the same as before. In this case, we're unlucky here. We picked some very short people here and here barely. Okay, and I think that's all I think. Oh, and here. So in general, here we were unlucky towards short people. Again, this is random. We just picked, we just repeated this procedure 40 times of picking 100 random people from the population. And in these 4 instances, the confidence interval actually did not include the population mean. And now finally, if we pick 1,000 people, the confidence interval is very, very tiny, but again, still with some probability, 5% probability, it does not include the population mean. So here again, we were unlucky on the shorter people side. So when I go back and I see here I had 40, out of those 40, 1, 2, 3, 4, 5, 6 confidence intervals did not include the population mean. So now you would do 6 divided by 120, and you will see that that's 5%. Okay, so essentially that's what it means. It means that when we have constructed this confidence interval, if we repeated the procedure 100 times, 5 of those times, the quantity of interest would not be included in the confidence interval. And 95% of the time it is. It makes you think, right? Because there's so many scientific articles about, you know, the cholesterol is like this, the cholesterol is like that. And if you pick 100 of those articles, for 5 of them, the quantity of interest is not going to be within the confidence interval that they give. Again, I mean, and that's why it's important for people to do follow-up studies and so on. All right, so what have we learned today? We have learned to build and interpret confidence intervals. Thank you very much.